If you're very familiar with partial differentiation, then you may not need this particular video. It'll be a review. But I figure there might be a few people out there who have never seen a partial derivative or could use a little quick review. So here's the idea. This is a multivariate function in two variables. Z or f of xy is equal to x squared y minus 2xy cubed minus 3x plus 4y. Alright, the idea is that here I have a function with two variables in it that makes it multivariate. And now if you've had multivariate calculus, which is traditionally calculus 3 in a semester system or calculus 4 in a quarter system, or if you're taking those now, then you've no doubt have seen this already. But multivariate functions have derivatives, but now it becomes complicated to think about a derivative. How would you do a derivative? Because this is a three-dimensional object. I have two deep independent variables, or input variables, x and y, and my output variable is z. And so it really describes a three-dimensional object, and it would be called a surface. And so z is a function of x and y, then being a function that has a single output for every input, that means it passes the vertical line test and all that stuff you study in earlier math. Except now it's a surface wandering around in three dimensions. So in three dimensions, we define the axis traditionally this way. The x-axis you have to pretend is coming straight towards you from the board. Obviously I can't do three dimensions on a two-dimensional board. But the x-axis comes straight out at you in the positive direction, and the negative it would go in. The y-axis goes side to side, and to the right would be the positive direction. Z-axis is your vertical, positive is up. So try to imagine some kind of object up here, maybe a sheet of some sort floating around, and that's a surface. And so suppose it's above us. So as I stand on the xy plane, that would be the floor. I can walk around the xy plane on the floor to different coordinates, and for each coordinate that's an input, and I go straight up to, or down as the case may be, to wherever the function is, and it intersects in a single point. The z value is the vertical. Alright, so that's a three-dimensional function, multivariate function. Of course, we can go with 4 dimensions, 5 dimensions, as many as you want to. And because in those calculuses we developed the tools to handle all those. But in this course we're going to stick with just the three-dimensional or two-input variable version here. Alright, now how would you do a derivative and what would it mean? Well, in 2 dimensions it's easy to tell what a derivative means because you learn that it's the slope of a tangent line on a curve. Well, here I've got a surface floating above me, and the way we interpret this, if we look parallel to the x-axis, say going straight out, if we look in that direction, parallel, then we've sliced our surface with a plane and we've created a curve, a two-dimensional curve in that direction. Then we can ask what's its derivative. That's called the partial derivative with respect to x. And we notate that this way. The partial derivative with respect to x uses this little symbol here. It's not really a 2, I don't know what it's called. I've never seen a name for it other than partial derivative symbol. We can also notate it partial of f with respect to x. And other notations would be z subscript x or f subscript x. So there's several ways to write what's meant by a partial derivative. And again, what it calculates is the derivative looking in the x direction. Well, how's that done? Well, it's done by assuming that y is constant. Because if we're looking parallel in the x direction, that means all the y values in that direction are constant. So suppose I shift over to y equal to 2, and look parallel to the x-axis, then all y values are constant, aren't they? So, in the general sense then, the partial derivative for this function is going to be 2x y minus 2y cubed minus 3. So let me explain that. If we let y be a constant, then I take the derivative of x squared and I get 2x times my constant y. This derivative is minus 2 times constant y cubed. This derivative with respect to x is negative 3, and that derivative, since y is a constant, it's going to be 0, so we don't write it. So that's f sub x, or partial respect to x. Alright, now if we wanted to do partial respect to y, and you can write it any way you want to here, as long as it fits one of these formats, partial respect to y of my function, same idea. Now I'm looking in the y direction, keeping x constant. So this derivative is 1 times x squared, 3y squared times minus 2x, so that's minus 6xy squared. This derivative with respect to y is going to be 0. That derivative is going to be plus 4. So that's the derivative in the y direction. Now, if you want to find a derivative in a different direction, not the x direction or the y direction, but somewhere in between, if you want to look out this direction, then we have to, it turns out we have a technique for that using, which employs vectors. So it's not germane to this course, but in case that was in your mind, yes, we can do a derivative in any direction. And that's a technique explored in one of those multivariate calculus courses. Alright, so that's the first derivative. Now, the second derivative is something we also have to consider here. Oh, telephone, timeout. Okay, now, where was I? We're looking at these partial derivatives. Here's the partial with respect to x, partial with respect to y. It makes sense to talk about second partial derivatives. And that plays a role in what we're about to do in differential equations. So the second partial derivative with respect to both x's would be notated something like this: partial squared of z respect to x squared. It can be written as fxx. You can use all those notations, but with two x's. And so this would be the partial respect to x of f of the first partial derivative. Alright, so the second partial derivative with respect to both x's is the partial of the first partial derivative. Alright, so if I take this partial derivative with respect to x, I'll get, again I'm treating y as a constant, so I'll get 2x. And this will be 0 and that will be 0, so I'm just done. It's 2x. Now we could do the second partial with respect to y, and I'll just call that fyy. And so it's the partial with respect to y of fy. So here I'm treating x as a constant. And we get, I think I've got a mistake here too. Let's go back to this one, because the partial of this with respect to x will be 2 times y. So this should be 2y. I'm treating y as a constant, but the derivative of 2x will be 2. Alright, so sorry about that. This should be 2y. Alright, please fix that. Okay, now then, here, if I take this partial derivative with respect to y, I'll get 0, and then I'll get this derivative is 2y times negative 6x, so that's minus 12xy, and that part will be 0. Alright, so that's the two second partial derivatives. Now we can also mix them, and they're called mixed partial derivatives. So if I did fxy, this would be the partial with respect to y of fx. So the order is x first and then y second. So I go back to this function, fx, and take its derivative with respect to y. Now I'm treating x as a constant. This derivative is 1 times 2x. So I get 2x, and then minus 6y squared. Minus 6y squared, that'll be 0. And then fyx, here the derivative with respect to y was done first, and then we do x, so this is the partial with respect to x of fy. Alright, so I go to fy and take its derivative with respect to x, and with respect to x I'll get 2x, and then this derivative is 1, so I get minus 6y squared, and then 0. Alright, so those are the 4 different second partial derivatives: xx, yy, xy, yx. Now here's something that's really nice. You notice that these two came out to be the same. And that's not a coincidence. It turns out if across the xy plane, if the if the function is continuous across I think it's a simply connected open domain or something like that. There's some technical details we'd have to read into here. It turns out that these two are always equal. So the only time they won't be equal is if you have something strange going on, like a disconnected region or something's not continuous in some place. But in general, and this is actually a theorem. I think it's called Clairaut's theorem. I'd have to look that up. Let me put that on here, and I hope I don't have the wrong name here. Clairaut's theorem says that these mixed partial derivatives are in general equal under the normal conditions that we would be thinking about. Alright, so this is a pretty important result, and it has quite a bearing on this topic we're about to get into in differential equations. And so, anyway, there's your introduction to partial derivatives, and now let's go apply them.